Okay, so we're continuing on with amines. And so last time we ended with a way to synthesize primary amines, which was called the Gabriel synthesis. So what we would do is we would take this molecule, which is succinimide, and that amide nitrogen is actually can be deprotonated by something as simple as hydroxide. So what we would do is turn this into a nucleophile, and that nitrogen then we could react with, and we really only react with primary amines. So any kind of primary alkyl chloride, alkyl bromide, but it has to be primary so that the succinimide nucleophile can come in, add to the carbon, and kick the bromine off so that we basically alkylate, add the alkyl group to the nitrogen. But this is really only going to work with a primary halide. So then we've got to get the nitrogen out of the succinimide, and so that's where we're going to find out that we talked about having different Y groups attached to the carbonyl. If that Y group is something like an OR group or an N group or a carboxylic acid group, bless you, or a chloride, these are all what are called carboxylic acid derivatives. And the definition of a carboxylic acid derivative is something that when you react it with H plus or hydroxide, and there always has to be water present as a solvent, that reaction will be called hydrolysis. So it'll be a cleavage with water. What we end up doing is we end up cleaving off whatever the Y group was. Bless you. And then we end up cleaving off the Y group, leaving the carboxylic acid behind, and then whatever that Y group was. So up here, if we take this and we react it with either H plus or hydroxide, and my preference would be to use hydroxide, then we'll end up cleaving off the now what has a different name in terms of a carboxylic acid, but we get the carboxylic acid and then we free up the amine. And I would prefer to use base, because if I used H plus, it's going to protonate the nitrogen and make it ammonium salt, which is going to be really, really difficult to get out of water. So this is what's called the Gabriel synthesis, and it's a sort of a traditional way of synthesizing primary amines. And the reason why I'm going back over that is because the computer ate my video in both classes, and this end part in both classes. So this way it's there if you didn't catch it the other day. Okay. All right, so that's our synthesis. We did alkylation. We reacted the amine with a primary or a secondary halide. And again, the thing there is that amines like to pick up protons, and so if we want a free amine, we got to keep it under basic conditions. So what else can we do? what else can we do is we can now react amines with what's called an azide. So we can take our, I'm going to take an alkyl halide and I'm going to react it with an azide, which is a nitrogen, 3 nitrogens with 2 triple bonds between them. There are 2 lone pairs at the end, and that puts the formal charges then. The center nitrogen is +1. The nitrogens on the end have 1, 2, 3, 4, 5, 6 valence electrons. They came with 5, so each one of those is a -1. So overall, the azide has a -1 charge. And the idea here is that we can react this with an alkyl halide and do an SN2 reaction on it. So one of the nitrogens then can take its lone pair and come in and kick off the halogen. So I can add this azide molecule to the end of the chain. And if we're figuring out our formal charges here, this nitrogen has 1, 2, 3, 4, 5, 0 formal charge. The middle nitrogen is still +1, and the end nitrogen is still -1, but overall now it's got a 0 formal charge. So this is going to be simply another nucleophile. Now, what can I do with this? Well, what I can do is write its resonance structure. And in its resonance structure, I want to create a leaving group. And the best way to create the leaving group out of an azide is to create a nitrogen gas molecule in it. So what I want is an N triple bond N at the end. So is that easy to do? Well, let's do this. Let's move that pair of electrons there. Will that violate anything? Probably. So maybe we shouldn't do that. Right, if I do that, then I'm violating octet rule. Because now, where'd it go? The nitrogen at the end is now going to have like more than 10 electrons. So I shouldn't do that. I shouldn't have done that. Okay, so let's erase that. Erase that. Erase it. Alright, we don't like that, so let's make it white. Okay, so we can't do that. We can't move the pair of electrons that way. So how about we do this? How about we move this pair of electrons here, and then we could probably move this pair of electrons. So if we move that pair of electrons there, we're going to have an N triple bond, but then this nitrogen is going to end up with what? It's going to end up with 5 bonds, so we got to move this pair of electrons here. So if we now move from the end, we're going to end up with nitrogen with 2 lone pairs, single bonded to a nitrogen with a triple bond, and then the nitrogen on the end. We still have to end up with a neutral formal charge. So this nitrogen is still +1, and now this nitrogen has 1, 2, 3, 4, 5, 6, so it's now -1. So what I've done in terms of creating this is, number one, I haven't violated the octet rule. But now I've created an N triple bond N, which is a great leaving group. So basically what I want to do is I want this molecule right here to leave. And so that's what we can do with an azide. So how am I going to make it leave? Well, what I'd like to do is to convert this that nitrogen into an amine. So as my nucleophile, how about I choose H minus? So my H minus comes in, attacks that nitrogen. This pair of electrons goes to that nitrogen. I lose N, triple bond N, so I lose nitrogen gas. I end up now with my nitrogen on the end, now picking up the hydrogen, and would still have two lone pairs that way. So now it's a negative. So now I can go ahead and add an acid or add water to it, so that now that N minus will pick up a proton, and so now I can make my amine. So that's how we can make an amine with an azide. And probably the best is going to be to use a primary or a secondary amine. Probably primary better than secondary. Okay. So all I'm doing is I'm just creating a leaving group out of the nitrogen. So that's another way of making an amine. There is no sort of systematic methodology here in this chapter. It's kind of just a big mess of reactions. So there really isn't, I don't know, there's no unifying theme in terms of transitioning from one to the other. It's sad, but that's the way it is for amines. That's why amines are like in the middle of carbonyls. Because we start talking about aldehydes and ketones, I set up the idea of carboxylic acids and derivatives, and I got to break it up with these amines. So, does that kind of make sense to everybody? Again, I'm just creating a great leaving group because I'm forming a nitrogen gas molecule. Okay, so that's using azides. There is another way to make amines, and we're going to find that we're going to do a lot of reactions with like organometallic reagents like Grignards and cuprates, and these are going to rely on us to remember our aldehyde and ketone reactions. And here's one. So you might say, okay, if I reduce this CN triple bond, I can make an amine, right? So how am I going to do that? You may say hydrogen gas. Well, what catalyst do I need? Because a CN triple bond might be really stable. But I can actually do this with just an H minus. So there's my H minus. Where did my H minus come from? Oh, I should have put that back here. Where did this H minus come from? Right, Grignards are C minus. What's the analog for H minus? You got two possible reagents. NaBH4 and lithium aluminum hydride. Which one's stronger? Lithium aluminum hydride is the stronger. So actually, that's what's used. We don't mess around with this. We use the strongest reducing reagent that we can. So we're going to use the stronger of the two, which is lithium aluminum hydride. I don't remember in the morning class if I I know lithium aluminum hydride is stronger because I walked into the lab years ago and one of my master's students says, oh, the bottle of lithium aluminum hydride caught on fire. And he wasn't freaked out, so I'm like, okay, how did you put it out? He's like, oh, I just threw sand on it. He was working in industry, which is exactly what you're supposed to do. Because if you throw water on something with a hydride, you make more hydrogen gas, and then you make the fire bigger. So when you just throw sand on it, it smothers it. So I know lithium aluminum hydride is stronger because when I use it, there's always that possibility it'll catch on fire. Sodium borohydride, never seen sodium borohydride catch on fire. So that's how I remember that one's stronger than another. So we need the strongest one. So over here, I need lithium aluminum hydride as my source of H-. So H- is going to be a nucleophile. What is it going to attack? Your choice is the hydrogen, the carbon, or the nitrogen. And the hint is hydrogen's a nucleophile. Take a guess. Aisha? Good guess. Yes. So the carbon is delta positive. The nitrogen is delta negative. The other R group is an R group. So a C triple bond, we're going to treat like a C double bond O. So the H- is going to come in and add to the carbon, and then what has to happen? The pair of electrons has to go to nitrogen to avoid having a 5 bond to a carbon situation. And so what did I just do? I added a hydrogen to the carbon. I've got a double bond, or I've got a nitrogen now with 2 lone pairs and a negative charge. What happens next? Nothing. It just waits for H+. Okay, so then I add H plus H2O, and that nitrogen gets protonated, and I've now made this molecule. Anybody psychic enough to tell me what my next question is going to be? No. How about what's that called? Starts with I. That is an imine. Are imines stable? No. Imines are not stable. So what happens when you react an imine with H plus and H2O? Carolyn? Not quite that. But it's going to go backwards. I forget. And apparently I'm not the only one. What do you make an imine out of? You make an imine out of a carbonyl and ammonia. So the imine in the presence of acid and water will go all the way back down to the carbonyl and ammonia. Except the problem here is, if I do that, I didn't make it amine. But what I'm doing is foreshadowing the fact that we're going to take some of these molecules and react them with C minus and H minus. We're going to make like hydrates, and we're going to make all those compounds that we made before that we said were unstable, and then when we add the acid and water, they're going to reverse themselves all the way back to the beginning. So this isn't helpful. Now, it will be helpful if I do what? If at this point I don't really add excess acid and water, right? So no excess acid and water. But now I could take this imine and I could make my amine out of it by doing what? I think we saw this last time. We took a carbonyl, we added an ammonia or a primary amine to it, we made a Schiff base or an imine out of it, and then what did I do? So then I could reduce this down by reductive amination by using hydrogen and palladium, and so I could reduce that down to the amine. So in this case, I could do the same thing. I could take my nitrile, react it with lithium aluminum hydride if I wanted to. I could then stop it at the amine and add H2 and palladium and take it down to the primary, or take it down to the amine. So nitriles we could go ahead and convert to amines as well by reductions. Carol? Would it be CH2? It would eventually be CH2, yes. Okay. So that's how we can, another method we can use to make amines, probably primary amines. Although from reductive amination we can make primaries and secondaries nicely. Okay, so that's all. That's great. Now let's talk about reactions of amines. So normally we talk about the reactions of amines that we know as review, which was the first half of the last chapter on aldehydes and ketones. In this one, it really wasn't, because we hadn't talked too much about how to make amines. But we started that last time. So now let's talk about reactions of amines. And let's go back to our friend, the electrophilic aromatic substitution. So if I wanted to add an electrophile to pyridine, which is aromatic, my question is, where does the electrophile add? Does it add to carbon A, or does it add to carbon B? Or I suppose we could say that it add to carbon C as well. So where should it add? A, B, or C? Well, unless you're like looking at that section of the Top Hat book, like I am on my little iPad, you probably can't. You probably wouldn't be able to guess. So how would I determine that? How did I determine it when we did electrophilic aromatic substitution on non-heterocyclic compounds? I added the E plus to what? What did I ask you to do on the exam? To add an electrophile to, like, the ortho, para, meta, and para positions. So if I added that E plus to A and wrote all the resonance structures, and then I added it to B and wrote all those resonance structures, and then I added it to C and wrote all those resonance structures, how do I know which electrophile it'll ultimately, where the electrophile will add? Michael? Whichever one has the most resonance structure, or the combination of resonance structures is the most stable. So that's how I can determine where E plus adds. So that sounds like a pretty tedious thing to do here. And I think our class time is more valuable. So I think we will make this a take-home quiz for Friday. So what would I like you to do? I'd like you to add E plus to A, write all the resonance structures. Add E plus to B, write all the resonance structures. Add E plus to C, write all the resonance structures. And then tell me which one has the most, or the most stable combination of resonance structures, so that we can figure out where the E plus should add. So we'll make that the take-home quiz for Friday. Now, I could, if I wanted, we could kind of do the same thing here, too, with the 5-membered ring. Because this is aromatic, too, right? Right, it is. So I could do the same thing here to determine whether the electrophile adds to either A or B. So maybe we should include that too. So try it with the 6-membered ring, and then try it with the 5-membered ring. Let's see if it adds to the same place. If the electrophile adds to the same place relative to the nitrogen or not. Does it add next to the nitrogen? Does it add one position away? What's the role of the 6-membered ring versus the 5-membered ring? And so ultimately, write all the resonance structures and then tell me where should the E plus add. So that way we can kind of figure this out ourselves. Okay. All right, so that's your take-home quiz. Because I could tell you the answer, but it'll last a little bit longer, maybe just a little bit longer, if you do it yourself. Okay. Let's move on to the two eliminations that are going to take a little bit of time to think about. So remember back last semester when we were taking an alkyl halide and we were treating it with something like a strong base, and we could form two different alkenes out of it. We could form these two products, A and B. So if we're doing an E2 reaction with a strong base and an alkyl halide, we could form product A or product B. It depended on the base, right? So I'm obligated to ask, if I wanted to form product A, what should my base be? So NH2 minus was the small base that could form either A or B, but since it can form either one, it's going to form the more stable one. And so that means that if I want to form product B, I should use terse butoxide. What did we call product A? What did we call the alkene that was the most stable? That's the Zaitsev product. Various spellings. Did we ever call B anything? Sometimes people will call B the Hofmann product. One F, two M's. And I thought it was Hofmann for a while, but I'm wrong. It's Hofmann. So people call this the Hofmann product because it's the less stable product, but I stay away from that because in order for us to understand what the Hofmann product really is, we have to get to now. So the Hofmann product then is when you eliminate and you form the least stable product. And so that's what we're going to talk about now, is Hofmann elimination. And so it doesn't do us any good last semester to talk about Hofmann elimination when it's going to be done with amines this semester now. So how do we do Hofmann elimination? Well, I already let the cat out of the bag. We're going to form the least substituted product as the major product. Okay. So if I said, what's the major product of Hofmann elimination? We already know the answer. Do we know why? Well, let's get to the reaction first. So in Hofmann elimination, what I'm going to do is we'll start with something simple. No stereochemistry. I'm going to take this amine and I'm going to react it with, I want to alkylate it to form an ammonium salt. So I'm going to react this with 3 equivalents of methyl iodide in basically kind of a basic solution. Because here's what's going to happen. I'm going to take my amine, I'm going to react it with my first equivalent of ammonia, first equivalent of methyl iodide. I'm going to add the methyl group to it. I'm going to make my ammonium salt, My iodide's going to be there as my counterion. And so then I'm going to have to treat this with base in order to make the free amine. So I'm just going to do an alkylation like I did last time. Alkylate it, remove the H+, and so then I'm going to do this step 2 more times with 2 more equivalents of methyl iodide. And so ultimately I'm going to end up with this. I'm going to end up with my nitrogen having 3 methyl groups added to it to form an ammonium salt. And so on the 3rd addition of methyl group, there's no H to remove. Now, why would I do that? I would do that because I wanted to turn the nitrogen into a good leaving group. And so the way to do that is to make it an N+, because now if I break this carbon-nitrogen bond and give the pair of electrons to the nitrogen, it can leave as a neutral molecule. Kind of like the way we protonated OH to make the oxonium ion to have it leave as water. So this is called an exhaustive alkylation, because I'm turning the nitrogen into an NR3+ with the other alkyl group that's attached. So now what I can do is now I can apply heat to this reaction. And if I apply heat to this reaction, I now have a leaving group attached to the alpha carbon. I got a beta carbon. I got another beta carbon. I got a beta hydrogen. Like that. And so I'm going to make this reaction go by heat. Now, which set of beta hydrogens am I going to lose? Am I going to lose A, or am I going to lose B? I'm going to lose A. Wait, how did you know that? Because I let the cat out of the bag by saying it was Hofmann elimination and we were going to get the least substituted product. Yes, exactly. Now you may say, well, why are you going to get the least substituted product? And that's a little more complicated reasoning. That could be another take-home quiz problem, but I think I've already given you, well, in your mind, I've given you too many, but this is based on the number of hydrogens that you can lose to do anti-periplanar E2 elimination. So let's just think about that a little bit here. So on this end carbon, the CH3, there are 3 hydrogens that I can orient anti-periplanar to the N+ group. Whereas over here on the B carbon or the B beta carbon, there's only 1 hydrogen that can be lost. So in terms of doing this elimination totally by heat, the major product is determined by how many hydrogens you can get into the anti-periplanar geometry. And so in this case, I have 3 hydrogens. Over here, I only have 1, so that means the major product is going to look like that. That's the major product. So in a way, what I'm doing is, by using heat as the only reagent, I'm forcing the molecule to basically look at the initial reactants. And to some extent, I'm looking at reactant to transition state, not the stability of the product. So the major product is totally dependent on the number of beta hydrogens.
Can you get the synthesis product using that?
Well, if I used a base, I could get the Satzev product. I mean, if I used a base at this point, then the base is going to... See, the base comes in and it grabs the hydrogen. In this case, by using heat, I've got to force the hydrogen and the leaving group to all leave at the same time. And so that mechanism then is going to be different because there's nothing pulling the hydrogen off of it. And you might say, well, can't the nitrogen just leave on its own and form a carbocation? It's not that good of a leaving group. So it needs help in leaving, but since there's no base, I got to heat it to make it move. I'll be honest, if I was Hofmann, I would not have gone, oh, well, I would never have drawn it out on paper like this to work that way. But a very few people ever do. They do the reaction. It's like, oh, it's backwards. So now I got to figure out why. And most times you die before you get the chance to figure out what happened. Somebody else later on does. So in this case, because I'm using heat and no base, I change the mechanism. And now our criteria for Hofmann elimination is which beta carbon has the most hydrogens. So that's the basis of Hofmann elimination, Michael.
Well, that has
What's left is this hydrogen comes in here, the N leaves, so I end up with a double bond, and there is no. It's that there's no methyl group there. So that's the correct one. So it's E2 elimination, no carbocation, no base. So it's now a third situation that we end up with. Now where this gets really interesting is if I give you a molecule with stereochemistry. Because then what you have to do is then you've got to rotate the molecule in the sawhorse projection in order to get the hydrogen and the leaving group to be anti-periplanar to get the right EZ stereochemistry of the final product. But we'll do that on Friday. Right? Friday, yes. On Friday. But what I want to do in my couple minutes left here is I want to show you another method to make nitrogen into a leaving group, and this one also produces the least substituted double bond, but instead of the molecule having to have the hydrogen and the leaving group anti-periplanar, I now have to have them coplanar. And so the way to do this is I'll just simply take if I take my nitrogen and I only add 2 methyl groups to it. Okay, so if I started out with if I started out with a molecule with NH2 on it, I would use 2 equivalents of CH3I. So I'm not going to exhaustively methylate it, I'm just going to give it 2. Then what I'm going to do is I'm going to treat this molecule with an oxidizing reagent. And I'm just going to put the oxidizing reagent for the moment in parentheses. And then I'm going to go ahead and give you a specific one, a peroxy acid. And so now what I'm going to do is now I'm going to change that nitrogen into this. So when a tertiary nitrogen gets oxidized, you put on an O- and the N becomes an N+. So this is actually what's called I'll tell you what it's called on Friday. It's not an oxime, but it's an oxidized compound. I'm slowly losing it. So, again, not really, but it's getting pretty close. So here's what happens, and then we'll talk about this more. So, now what happens is this O- comes over and grabs the beta hydrogen. They're all in the same plane. Then this pair of electrons moves here, and then that pair of electrons goes to the nitrogen. And the carbon that's going to remove the hydrogen will be the one that's least substituted. And so this elimination, again, also produces the least substituted double bond. But now instead of the beta hydrogen in the leaving group having to be anti-periplanar, they now have to be coplanar. Because I'm going to form this 5-membered ring transition state. And what this is called cope elimination. So cope and Hofmann elimination each give us the opportunity to form the least substituted double bond. But when we get into the details of stereochemistry, what we're going to find is that when I lose the hydrogen and the N+ anti-periplanar, that's a different easy product than if I lose the hydrogen and the amine oxide. When I lose the amine oxide product, I'm going to get a different easy product. So again, the idea here is I'm building up all the possible reactions to be able to do that. That's what that's called. That's an amine oxide. There's some things that have escaped, but they haven't quite made it away. All right, so there you have your take-home quiz problem for Friday. Remember, the problems of ketones and aldehydes are due on Monday from Top Hat. So if you have questions, come and see me, which apparently a lot of people are doing today. So otherwise, we will continue this on Friday.